Hey there, and welcome. You found the corner of YouTube where we don't sprint through facts or speed toward quick conclusions. Here we give big, fascinating questions the room they deserve, letting curiosity stretch its legs without a stopwatch ticking in the background. This isn't the place for rapid-fire bullet points. Instead, we take our time, letting each thought breathe so we can really explore the strange, mesmerizing, and sometimes unsettling truths that our universe keeps tucked away in plain sight. Tonight we're diving into an idea that's been quietly lingering at the edges of both science fiction and astronomy for years. It's rarely talked about in depth, but it's been there all along, the notion that Earth, this world beneath our feet, this seemingly singular home we think of as special and irreplaceable, might not actually be unique in the way we imagine, not in terms of beauty or meaning, but in terms of existence. That perhaps long before us there were countless other worlds much like this one, with seas, skies, and maybe even life, and that many of them simply didn't make it. It's an unsettling thought. We like to imagine our planet as the lucky miracle, the single winning ticket in a hostile, indifferent universe. But what if that story is only part of the truth? What if Earth isn't one in a billion, but simply one of the few survivors left from a galaxy littered with failed attempts? Imagine, scattered across unimaginable distances, the husks of worlds that once tried to do what ours has done, but fell short and faded away. Before we wander deeper into that thought, take a moment and notice where you are right now. Not just the country or city, but the exact spot you're sitting or standing in. Are you inside, surrounded by the hum of appliances, or outside, catching the rustle of leaves or the faint rumble of far-off traffic? Is sunlight spilling across your floor, or is the night sky stretched above you, maybe dotted with stars, or perhaps hidden behind the orange glow of city lights? Hold that image in your mind for a second, because every detail of it, the air you're breathing, the solid ground beneath you, the familiar sounds, is bound to this one world. This thin shell of rock, water, and atmosphere has been our only home for the entirety of human history. Every single second of your life has played out right here. That alone can be grounding. But it can also shift how we see things, because if this is the only place we've ever known, it's easy to assume it must be rare. We can't step onto another planet and feel a different wind on our skin, so our sense of what's possible is shaped entirely by Earth. Telescopes can show us distant worlds. Spacecraft can send back images. We can detect planets orbiting other stars. Thousands of them, with likely billions more out there, but they remain abstract, almost like myths. And with myths, we tend to simplify. We imagine only two categories, dead, barren rocks or perfect gems like Earth. But the more we learn, the more it seems there's a massive, overlooked middle ground. Planets that began with potential, worlds that may have reached a point of thriving before everything changed. If life can emerge in more than one place, then it stands to reason that not all of it will survive. There's no cosmic law that guarantees once life starts, it will keep going. Stars age and flare, atmospheres thin, and escape. Temperatures swing violently, collisions and catastrophes happen, and even the most adaptable life has its limits. When those limits are broken, the chapter for that world ends, leaving nothing but the quiet remains of another failed experiment in the universe's vast archive. We don't have to look far to see possible examples. Mars may have once had flowing rivers and a thicker sky. Venus could have been wrapped in oceans before becoming a furnace. Even some of our solar system's moons, like Europa and Enceladus, hide oceans beneath their icy crusts, perhaps once alive, perhaps still holding secrets. These aren't lifeless from the start. They're what you might call almost worlds, and that's just in our own backyard. If we can find so many nearby, how many more are scattered across the Milky Way? It's tempting to find this line of thinking grim, but there's a kind of awe in it too. It hints that life isn't just possible, it's persistent, that it's tried over and over again in places we'll never see. There may have been civilizations that rose and vanished, oceans that swelled and dried, forests that flourished under alien skies. And somehow, in the midst of all that, Earth has lasted this long, not because it was destined to, but because so far the conditions have aligned in our favor, and catastrophe hasn't claimed us. Before we go too far into the silent histories of distant planets, think about this. If you could stand on the surface of one of these other worlds, Even knowing it's lifeless now, would you? Would you want to see the last traces of what was there? Or would you prefer to leave it to the imagination? There's no right answer, but thinking about it might give you a sharper sense of just how rare our moment here really is. And if you've stayed with me this long, following this slow, careful unfolding of an idea, I have one small request. If you appreciate this way of exploring, one that doesn't rush to the point, but instead sits with the questions, consider leaving a like. It helps keep the conversation going, and it lets me know you're out there thinking about these things too. If you're enjoying this slower, more deliberate way of exploring ideas, consider liking this video or subscribing. It's a small action, but it keeps this space alive so more curious minds can join these quiet journeys. So here we are, standing on a living, breathing planet, yet surrounded by the possibility that it's just one of the few survivors in a universe full of vanished worlds. And to truly start grasping that, we have to look beyond the familiar blue dome above us, out toward places that may once have been alive but aren't anymore. From the ground, it's easy to forget how fragile Earth really is. Our daily view is so close up, the streets we walk, the trees that shade us, the skyline above. Even the horizon feels endless, until you remember that on a cosmic scale, it's just the curve of a sphere less than 13,000 kilometers wide. But pull far enough away, and the image changes. From the moon, Earth becomes a luminous marble floating in blackness. From the outer planets, it's a pale dot small enough to hide behind your fingertip. From the vastness between the stars, even that dot disappears entirely, and every moment of human history is reduced to a point too small to see. That kind of perspective can take the edge off our belief that Earth is central to the story. It doesn't have to make us feel unimportant, though it might, but it does remind us that our chapter is just part of a much bigger book. And in that book, Earth might not be the singular protagonist we imagine. It could be just one among countless planets, each with its own fleeting role in the universe's timeline. Thinking of it that way makes the idea that we're the only success story feel less like a certainty and more like a lucky hand in an impossibly big game. Astronomers have spent decades trying to answer the question of how common planets like ours really are. For most of human history, it wasn't even something science could measure. We knew of the worlds in our own solar system, but beyond that, stars were just distant lights with no visible companions. The first confirmed planet orbiting another star wasn't discovered until the early 1990s. Since then, the count has soared into the thousands, and almost every month brings new additions. Many are nothing like Earth, massive gas giants, molten infernos, frozen spheres, but some are surprisingly familiar in size and orbit, even falling into what scientists call the habitable zone, the distance from a star where liquid water could exist. The name can be misleading, though. The being in the habitable zone doesn't guarantee a planet is truly habitable, just that it could be if everything else works out. A planet could sit at the perfect distance, yet have no atmosphere, or one laced with poison. It could have pleasant temperatures, but no magnetic field to protect it from deadly radiation. It might have oceans, but no land, or land without a drop of water. The right combination of factors that allows life to begin and keeps it going is far harder to achieve than it sounds. Earth, in this sense, is balanced on a razor's edge. Any closer to the sun, and we'd bake like Venus. Any farther, and we'd freeze like Mars. A smaller planet might have lost its air to space. A larger one could have ended up with crushing surface pressure. Even the tilt of our axis, the size of our moon and the gravitational presence of Jupiter, which helps divert dangerous asteroids, all play their part. The deeper we study planets, the more it feels like survival depends on checking off a long, improbable list. Yet with so many stars and planets in existence, it's likely that at least a few others have met the criteria. And if some of them are gone now, the question becomes, what erased them? Were they victims of forces no life form could prevent, like a star's slow brightening or a catastrophic impact? Or did they undo themselves, life pushing their own worlds past the point of no return? It's hard to picture until you put it in familiar terms. Imagine standing on an earthly shoreline, waves rolling in and out, storms passing overhead, the coast shifting over centuries but still feeling stable. Now imagine that same coastline on a planet where the ocean is gone. The rocks are the same, the shape of the bay remains, but the air is thin or poisonous, and the light from the star feels alien. It could still be beautiful, but it would carry the hollow stillness of a place that used to live. That's what a failed world is. Not necessarily shattered, but stripped of the ability to support what it once did. In our own neighborhood, Mars tells this story best. We can see dried riverbeds, minerals that formed in water, and polar ice caps. Billions of years ago, it may have had a thick atmosphere and a warmer climate, but the planet's core cooled, its magnetic shield faded, and solar winds peeled away its air. Water either froze deep underground or escaped into space. If life ever existed there, its window was closing fast. Today, Mars is a frozen desert, its history buried in dust and stone. Venus offers a different warning. It may have once been covered in oceans, but its closeness to the sun, combined with a runaway greenhouse effect, turned it into a hellscape. Its heavy atmosphere is almost pure carbon dioxide, trapping so much heat that the surface is hot enough to melt metal. Clouds of sulfuric acid swirl above, and the crushing pressure is over 90 times what we experience on Earth. Whatever hope Venus once had was erased by an unstoppable chain reaction of heat and chemistry. Both of these worlds remind us that simply starting in the right place isn't enough. Conditions shift, sometimes gradually, sometimes all at once. A planet can seem safe for hundreds of millions of years, then cross a tipping point it can never return from. That's part of what makes Earth's long habitability so extraordinary. We've endured asteroid strikes, ice ages, and climate swings that might have ended life elsewhere. But when we scale our view up to the entire galaxy, the picture only gets more intricate. Some stars are far more temperamental than others, unleashing sudden blasts of radiation powerful enough to strip a planet's atmosphere in moments. Some planets live in unstable neighborhoods, their orbits slowly tugged and twisted by nearby giants until they're thrown off course entirely. Others form in crowded regions, dense star clusters or near the chaos of supernovas, where destructive events are not just possible but likely. The truth is, the conditions that let life begin are fragile, and those that let it endure are rarer still. If you pictured the galaxy as a single landscape, it wouldn't be a smooth plain scattered with a few bright oases. It would be rugged and unpredictable. Deep valleys where life never stands a chance, high peaks where it burns out too quickly, and occasional plateaus where the balance holds just long enough for life to grow. Earth may be resting on one of those plateaus right now, but plateaus don't last forever. Over millions or billions of years, climates shift, continents drift, and stars evolve. Our own sun will one day swell into a red giant, roasting or swallowing the inner planets. But long before that happens, Earth's delicate balance will change in ways we might not be able to reverse. That's why it's entirely possible that many planets we would have called Earth-like in their golden age are now past their prime. From a distance, they may still look perfect. The right size, the right orbit, but up close, their time has passed. They're like houses with the porch light still glowing but no one left inside. And if the galaxy is old enough for this cycle to have played out countless times, then it could be filled with such worlds, silent reminders that habitability is always temporary. But this idea doesn't have to leave us hopeless. In fact, it should make us value what we have right now even more. The fact that Earth is still within its narrow survival window means we're living through something that might not be common at any given moment in the universe's history. It also means we have the rare privilege and responsibility to protect it from joining that long, invisible list of lost worlds. Many planets never got the chance. Some may have had the chance but didn't recognize it until it was too late. We do. And this is where our real exploration begins, into the life and death of planets. Because to understand Earth's future, we first have to understand what causes worlds to fail. That starts with looking at the cautionary tales close to home, and then expanding outward to see the larger patterns across the galaxy. If you could step outside the Milky Way and look down on it from above, you'd see a vast spiral of light, hundreds of billions of stars dusted across great arcs of gas and shadow. At first glance, it would feel inevitable that life must be everywhere. But between those glowing points would be vast stretches of darkness. Hidden in that darkness are places that once thrived in ways we can barely imagine, and are now nothing more than ruins. You could think of them as entries in a cosmic cemetery, unmarked graves scattered across unimaginable distances. Cosmic graveyard isn't a term astronomers use. They prefer words like uninhabitable or sterile, but graveyard feels more honest. It implies something was lost, that there was a before and an after. And the haunting truth is that many of the planets we observe today may belong to this category. We just can't recognize them as such, because we only arrive for the final chapter of their story. Some of these worlds never stood much of a chance, forming too close to their stars and cooking from the start, or too far out and freezing solid before life could take hold. Others circled stars that lived fast and died violently, swelling into giants or exploding in ways that erased any possibility of survival. But the most unsettling members of the graveyard are the ones that seem to have it all: the right size, the right orbit, the right conditions, and still didn't last. We have two striking examples right here in our solar system. Venus and Mars are the graves we can visit most easily, and their stories are sobering. Venus shows us what happens when stability tips toward heat, a runaway greenhouse effect where carbon dioxide traps more warmth, releasing even more CO2 in a feedback loop that spiraled into catastrophe. Once that cycle began, there was no going back. Mars tells the opposite story. Its magnetic shield collapsed, its atmosphere thinned, and its warmth bled into space. Water either froze beneath the surface or vanished entirely. In both cases, the planets crossed a threshold they could never return from. And these are just the ones we can study up close. The thousands of exoplanets we've found tell us the variety of failure is vast. Many orbit so near their stars that they're locked in place, with one side locked in eternal daylight and the other trapped in endless night. The day side bakes, the night side freezes, and only a thin band between might be tolerable, but never enough to sustain a global biosphere. Others are massive gas giants without a surface or bare rocky worlds stripped of their atmospheres by relentless stellar winds. Then there are the so-called super-Earths, planets larger than ours, some sitting in the habitable zone. They sound promising, but many are likely covered entirely by deep oceans with no land, or shrouded in atmospheres so thick and heavy that their surfaces are alien and hostile. Some may have once been true havens, only to lose their balance when their stars changed, or when their own geological processes turned against them. One of the more sobering lessons in planetary science is this: even if life exists on a planet, there's no guarantee it will still be there a billion years later. Stars brighten with age, slowly altering the energy their planets receive. Continents drift, reshaping currents and climates. Even the chemistry of the air can shift over time, and on Earth, life itself has been one of the biggest agents of change, filling the atmosphere with oxygen, cooling the planet, and transforming the surface in ways that would be unrecognizable to any alien visitor from our deep past. So far, those changes life has brought to Earth have worked in our favor, but there's nothing in the cosmic rulebook that says it will always be that way. On another planet, the influence of life could tip the balance in the opposite direction, setting off a chain reaction that slowly, or suddenly, makes the world less welcoming. The planetary graveyard doesn't only hold the quiet losses. Some worlds likely ended in instant catastrophe. A massive asteroid strike could wipe out ecosystems in days. A nearby supernova could blast a planet with lethal radiation, shredding its atmosphere and sterilizing its surface. A gravitational nudge from a larger neighbor might throw a planet into wild, unlivable seasons, or even hurl it entirely out of its star system. Picture a lush world of oceans and forests drifting alone in interstellar space, its seas freezing solid in the endless night. Life there wouldn't fade gently, it would stop abruptly. These scenarios sound extreme, but on the scale of the universe, they're not unusual. Planets are born in restless environments, sharing space with other bodies that pull on them, colliding and reshaping their paths. They orbit in galaxies where stars are constantly being born, burning bright and dying violently. We just happen to live in a relatively calm era and a peaceful patch of space for now. But here's something to consider. The graveyard might not be final for every world in it. Some planets could, at least in theory, come back from the brink. A frozen rogue planet wandering through space might pass close enough to a star to thaw again. A world stripped of its atmosphere might build a new one through volcanic eruptions or comet impacts. Whether life could re-emerge in those conditions is a much bigger question, but if habitability can fade, maybe it can return too. If so, the graveyard is less a fixed cemetery and more a shifting archive, with some entries possibly waiting for a second chapter. Still, for most planets, the end is permanent. A runaway greenhouse effect won't undo itself. A planet consumed by its star won't reappear. A collision that shatters a world leaves only debris fields drifting forever. And even if the surface survives, the death of its biosphere marks the loss of everything that made it alive. When we talk about dead planets, what we're really describing is the end of possibility. They may remain beautiful in their own haunting way, but they no longer hold the chance for something to grow, change, or thrive. The reason the idea of a planetary graveyard feels so powerful is because it reframes planets as characters in a story, each with a beginning, a middle, and an end. Earth is somewhere in its middle chapters, still full of oceans and forests, still alive in every sense we know, but the middle is never the end. And if there's anything we've learned from the examples around us, it's that endings take many different shapes. Our challenge is that we rarely get to see a planet's full arc. We arrive in the story too late to witness its beginning, and often too late to understand exactly how it ended. That's true for Mars and Venus, and it will be true for almost every exoplanet we study. Even with the most advanced telescopes, we're reading gravestones with missing inscriptions, and there's a kind of humility in that, a reminder that the universe doesn't shape its timelines for our convenience. We may want tidy answers, clean causes, and clear outcomes, but the graveyard offers only fragments and patterns, never a perfect record. So when we think about the planetary graveyard, it's not just cosmic archaeology, it's also a warning and a reflection. It shows us the many ways a world can fail, and it forces us to ask where we fit in that long procession. Are we an outlier destined to last while others fade? Or are we simply walking the same path toward an ending we'd rather not imagine? The only way to begin answering is to study the individual stories of those lost worlds, to see what their fates might reveal about our own. And the most revealing stories aren't always in distant star systems. We don't have to scan half the galaxy to find examples of ghost worlds. Some are right here in our solar system, orbiting the same star we do, sharing our cosmic neighborhood. They're close enough that we've photographed them in extraordinary detail, sent spacecraft to orbit them, and even landed machines on their surfaces. And the more we've seen, the more they feel like abandoned ruins in our own backyard, places that may once have been alive in some form, now left as silent shells. Mars, Venus, and several of the moons in our solar system fit this description. Each followed a different path to desolation, and together they form a kind of guidebook for how a planet can move from promising to barren. Because they're so close, these are the worlds we know best, though even here, mystery outweighs certainty. Mars is the most famous of these ghosts, partly because of how much it mirrors Earth in certain ways. Smaller, colder, and far drier now, it still has valleys, mountains, ice caps, and what look like ancient riverbeds carved into its surface. These features hint at a past far different from the frozen desert we see today, a time when liquid water may have flowed freely, pooling into lakes and seas. Data from orbiters and rovers backs this up, revealing minerals that only form in water and pointing to a thicker atmosphere and warmer climate in the past. The leading explanation is that Mars lost most of its atmosphere when its magnetic field collapsed. Without that invisible shield, the planet was defenseless against the solar wind, a constant stream of charged particles from the sun, which gradually stripped the air away over millions of years. As the atmosphere thinned, the warmth escaped and the water vanished, either freezing underground or bleeding into space. As Mars's atmosphere thinned, the pressure at its surface dropped, and its water either froze solid or escaped into space. If life ever began there, it would have faced an increasingly unforgiving world until the chance for survival vanished completely. Today, the planet still clings to water, but it's trapped in polar ice caps and perhaps hidden in salty underground lakes. The surface itself is bone dry, battered by radiation, and nearly impossible for anything to survive on. Yet the traces of its wetter past remain etched across the landscape, like faded carvings on an ancient monument. Venus tells a very different ghost story, one of too much heat instead of too little. Nearly identical to Earth in size and composition, Venus may once have enjoyed a mild climate and vast oceans, but being closer to the sun meant it received more energy, and over time, that extra heat sparked a runaway greenhouse effect. Water in its skies was lost to space, carbon dioxide built up, and temperatures soared. Today, the surface is hot enough to melt lead, the air pressure is crushing, and clouds of sulfuric acid drift overhead. Any hope for life as we know it was erased long ago. What makes Venus truly unsettling is the possibility that it remained Earth-like for hundreds of millions of years before spiraling into this furnace. A reminder that a planet can seem stable for ages before crossing a point of no return. If Mars and Venus are cautionary tales about how fragile a planet's balance can be, the icy moons of our solar system are a reminder that habitability can take shapes we might not expect. Europa, one of Jupiter's moons, hides a global ocean beneath an icy shell. Saturn's moon Enceladus sprays plumes of water vapor from cracks in its surface, hinting at seas below. Titan, another Saturnian moon, has rivers and lakes of methane and ethane beneath a dense atmosphere that could shield life from deadly radiation. These moons aren't dead in the same sense as Mars or Venus. Some could even harbor life, but if they do, it's likely deep beneath their surfaces, far from the sunlit environments we usually imagine. They show us that appearances can be deceiving, and that the line between a failed world and a living one may be invisible to us. Studying these nearby examples is far more than planetary sightseeing. They are case studies, lessons in the many paths a world can take. If we can learn exactly why Mars dried out, why Venus overheated, and whether the icy moons shelter life, we'll have a clearer picture of just how rare Earth's stability might be. We'll also sharpen our ability to spot habitable worlds elsewhere, and the warning signs that one might be on the verge of collapse. It's impossible to examine these worlds without a sense of reflection. Mars, with its dry riverbeds, is a glimpse of what Earth might look like if we lost our atmosphere. Venus warns us of what could happen if greenhouse gases spiral out of control. The icy moons suggest that life can endure in unexpected refuges, even when a planet's surface seems utterly inhospitable. Together, they form a cautionary map, not a prophecy, but a set of possibilities. What's striking is the variety of fates we see just within this single solar system around a single star. Multiply that by the hundreds of billions of stars in the galaxy, and the number of potential ghost worlds becomes staggering. Some would bear obvious scars, blasted by impacts, scorched by heat. Others might look calm and beautiful, hiding the fact that their living days ended eons ago. If this is what we find in our own neighborhood, it's a reminder that Earth's place in the story is far from guaranteed. Right now, we're in the middle of our planet's habitable window, but windows close. The ghost worlds next door show just how fast a planet can shift from thriving to barren in geological terms. Once that threshold is crossed, it's rarely reversed. These neighboring planets and moons aren't just targets for exploration known, they're mirrors reflecting back the reality that the conditions we enjoy are neither universal nor permanent. So the question isn't only how many planets are alive today, but how many once were, and what their stories mean for our own. That question becomes even more urgent when we remember that our solar system is only one grain of sand on the endless shore of the galaxy. Beyond our sun's reach are countless other stars, each with its own worlds. If we've already found ghosts among our closest neighbors, how many more are waiting out there, silent and unknown? The only way to find out is to keep looking, to push deeper into the uncharted, searching for the same signs of past life we've learned to read here. Mars, in particular, has fascinated humanity for as long as we've been watching the night sky. Even without telescopes, ancient observers noticed its reddish hue and unusual path among the stars, naming it for gods of war and strength. In more recent centuries, it became the leading candidate for another Earth, a place that might host life or might once have done so. Over the years, our hopes for Mars have swung between seeing it as a living neighbor and dismissing it as a dead desert, but as the evidence has grown, the truth appears to be somewhere in between. Mars today may be lifeless on the surface, but the evidence suggests it was once far more welcoming. Interestingly, the first hints didn't come from spacecraft at all, but from telescopes. In the late 1800s and early 1900s, astronomers like Giovanni Schiaparelli and Percival Lowell claimed to see long, straight markings on the planet's surface, which they described as canals. The term lit a spark in the public imagination, inspiring visions of advanced Martians building massive waterways to carry water across a dying world. We now know those canals were nothing more than tricks of the eye, but the idea of a living Mars never really left popular culture. When robotic probes finally visited, the truth turned out to be less sensational, yet far more intriguing. Mars does indeed have channels and valleys stretching hundreds, even thousands of kilometers, but they were carved by ancient rivers, not alien engineers. NASA's Mariner missions of the 1960s and 70s sent back the first close-up views, revealing a surface dry and cratered like the moon. For many hoping for lush landscapes or bustling alien cities, it was a letdown. But scientists soon realized that this dry, dusty planet still held remarkable secrets. The Viking orbiters and landers in the late 70s revealed branching valleys, floodplains, and layered deposits, all pointing toward a watery past. Over the decades, with the help of newer missions like Mars Global Surveyor, Mars Odyssey, and a fleet of rovers, the picture became clearer. Billions of years ago, Mars likely had a thicker atmosphere, a warmer climate, and large bodies of liquid water. One of the strongest clues comes from the minerals in its soil, clay and hydrated salts that form only in the presence of water. Their existence suggests that Mars once hosted lakes, rivers, and perhaps even seas. Inside Gale Crater, explored by the Curiosity rover, layered sediments look strikingly similar to those left behind by ancient lakes on Earth. Some of these layers extend for kilometers, recording cycles of wet and dry periods over millions of years. If life ever emerged on Mars, these lakes would have been prime habitats. So what went wrong? The leading explanation points to Mars's size and its internal heat. Being smaller than Earth, it cooled more quickly. As its core cooled, it stopped producing the magnetic field that once protected its atmosphere from the solar wind. Without that shield, the planet's air was slowly stripped away. As the atmosphere thinned, surface pressure dropped, and liquid water could no longer remain stable. It either froze underground or evaporated into space. Over millions of years, Mars shifted from a warm, wet planet to the cold desert we see today. If life ever existed there, it would have been forced underground, perhaps surviving only in small, protected pockets. The idea isn't far-fetched. Recent detections of methane in the Martian atmosphere have stirred speculation. On Earth, methane is often linked to biological activity, though it can also be produced by geological processes. The fact that methane on Mars seems to rise and fall with the seasons suggests something active is happening beneath the surface. Subsurface water, detected as ice, and possibly even salty liquid lakes, could provide a refuge for any surviving microbes. For now, though, we have no direct proof. What we do know is that Mars was likely habitable billions of years ago, making it one of the most compelling places to search for life beyond Earth. Finding fossilized microbes or even chemical traces of ancient biology would be a game changer. It would prove that life can arise on more than one planet in the same solar system, greatly increasing the odds that it exists elsewhere in the galaxy. But it would also remind us that habitability doesn't last forever, and that even a promising world can lose its grip on life. What's fascinating about Mars is how much it may have resembled Earth early on. Both formed from the same swirling cloud of dust and gas. Both had volcanoes, atmospheres, and liquid water. For a time they might have been near twins, each with the potential to support life, but their paths diverged sharply. Earth's magnetic field held strong, its atmosphere stayed thick, and its climate remained in the narrow range where water could persist on the surface. Mars, on the other hand, cooled too quickly, lost its shield, and became a frozen desert. How long Mars remained habitable is still uncertain. It could have been a few 100 million years or more than 1 billion, either way, in cosmic terms. That's a blink of an eye. If complex life takes billions of years to evolve, Mars may never have had the time it needed. That raises an intriguing possibility. Maybe the universe is filled with planets where life begins, but never has the chance to advance beyond its simplest forms. Worlds where microbial colonies form, ecosystems begin to take shape, and then everything is cut short by climate shifts or geological changes. From a distance, Mars still looks inviting. It's not scorched like Venus or locked in perpetual ice like some outer moons. Its sky is tinted orange, its mountains tower above any on Earth, and its canyons cut deeper than the Grand Canyon. If you stood there in a spacesuit, you might almost forget how inhospitable it really is. But the air is too thin to breathe. The temperatures can plunge low enough to freeze carbon dioxide, and planet-wide dust storms can shroud the surface in darkness for weeks. Mars is beautiful, but it's also a stark reminder that beauty alone doesn't guarantee survival. What we see today is the final chapter of a planet's long decline. Its rivers have vanished, its seas have evaporated, and its once protective atmosphere has thinned to a whisper. Even now, Mars holds the memory of its younger, more vibrant self in its rocks and dust. Every track left by a rover's wheel, every scoop of soil lifted by a robotic arm, is like uncovering a fragment of a planet that almost succeeded. Mars challenges us to think about how close a world can come to being Earth-like, yet still end up empty and silent. It's also a reminder that planets are not static. What's true today won't always be true tomorrow, not over the long arc of time. Earth's own climate, atmosphere and oceans have shifted dramatically over billions of years, and they'll keep changing. The difference so far is that our planet has remained within that delicate range where complex life can survive. Mars fell out of that range long ago, and we're still piecing together exactly why. If humans eventually set foot there, they'll be walking across the remains of a place that once had rivers under blue skies, and possibly life before Earth's own biosphere had even begun to form. They'll stand under a paler sun, feel the thin bite of its air, and know they're walking through one of the clearest reminders of just how fragile a habitable planet really is. This is why Mars is more than just another science target. It's a story still unfolding, a case study in how worlds evolve, and a warning that once habitable does not mean forever habitable. The more we learn about how and why Mars changed, the better we may understand how to keep Earth from following the same path. And that brings us naturally to its neighbour in the solar system's gallery of ghost worlds, a planet that didn't freeze into silence like Mars but burned itself into a furnace. If Mars is a lesson in what happens when a world loses too much warmth and air, Venus is the opposite extreme, a place that kept both but in the wrong proportions and paid dearly for it. In size, mass, and basic composition, Venus is close enough to Earth that we often call them planetary twins. Early planetary scientists even imagined it might share our habitability, with oceans, clouds, and a steady, life-friendly climate. Instead, it has become one of the most hostile places in the solar system. On Venus, the surface is hot enough to melt lead. The pressure is like standing nearly a kilometer underwater. The air is thick with carbon dioxide and clouds of sulfuric acid swirl above. What makes Venus fascinating isn't just how extreme it is now, but that it almost certainly didn't start this way. Many scientists believe that billions of years ago, Venus may have been temperate, with liquid water covering parts of its surface. Given its similarities to Earth, it's likely both planets began with comparable amounts of water and similar atmospheric compositions. The difference came down to what happened next. Position is key. Venus orbits about 30% closer to the Sun than Earth, meaning it gets nearly twice as much solar energy. On Earth, the balance between sunlight coming in and heat escaping out keeps the surface in a range where liquid water can exist. On Venus, that extra energy may have tipped the scales. As the planet warmed, more water evaporated into the air, and because water vapor is a powerful greenhouse gas, it trapped even more heat. This created a feedback loop. Higher temperatures cause more evaporation, which caused more heat trapping, which caused still higher temperatures. Over time, the oceans boiled away. Water vapor high in the atmosphere was broken apart by solar radiation, and the lighter hydrogen atoms escaped into space. Without water to absorb carbon dioxide or help weather rocks, CO built up in the atmosphere. Today, carbon dioxide makes up roughly 96% of Venus's thick, choking air, creating an incredibly efficient heat trap. The result: surface temperatures around 465 degrees Celsius, hotter even than Mercury, despite Mercury being closer to the Sun. Above that blistering surface, the clouds add another layer of hostility, composed mainly of sulfuric acid droplets. They reflect much of the sunlight that strikes the planet, making Venus brilliant in the night sky, yet completely hiding its surface. For centuries, this dazzling brightness inspired myths and legends. The ancient Greeks and Romans linked Venus to their goddesses of love and beauty. The Maya tracked its movements with precision. To the naked eye, it's a steady jewel-like light, second only to the moon. but its beauty is a mask. Beneath it lies a place that can destroy a spacecraft within hours and a human in seconds. Our visits to Venus have been short and punishing. In the 1970s and 80s, the Soviet Venera landers touched down and survived for no more than about 2 hours before succumbing to the crushing pressure and searing heat. The photos they returned showed a barren, rocky plain under a yellow sky. No oceans, no vegetation, just a desolate wasteland. Later, NASA's Magellan orbiter in the 1990s mapped the planet with radar, revealing a landscape of vast plains, towering mountains, and thousands of volcanoes. Some of those volcanoes may still be active, releasing gases that feed the planet's oppressive atmosphere. One of the most unsettling truths about Venus is how long it might have stayed friendly to life before its downfall. We still don't know exactly when it shifted from potentially habitable to utterly unlivable. Some climate models even suggest Venus could have supported liquid water for hundreds of millions, maybe even billions of years, if its early rotation rate or atmospheric composition had been slightly different. If that's true, life may have had a genuine chance there. And that's the part that lingers. Even a planet that gets everything right for a very long time can still lose it all. There's no universal rule that keeps a planet safe forever, and for Earth that's a sobering thought. We may sit farther from the Sun than Venus and have a different atmospheric history, but the same physical processes that turned Venus into a furnace, runaway greenhouse warming, water loss, and shifts in atmospheric chemistry, are governed by the same laws everywhere. The difference is a matter of degree, and that means the margin between stability and collapse may be much thinner than we'd like to think. Venus also complicates how we hunt for life on worlds far beyond our solar system. From light years away, a Venus-like planet could easily masquerade as an Earth twin. It's about the same size, wrapped in a thick atmosphere, and might appear to orbit in the so-called habitable zone. Without detailed data on its air and surface conditions, we could mistake it for a welcoming world. That's why understanding Venus matters. It's the blueprint of a failed Earth and a warning against false optimism when studying distant planets. And then there's another reason Venus captivates scientists, the lingering question of whether something might still live there, not on its scorched surface, but in its clouds. Around 50 kilometers above the ground, the air pressure and temperature are surprisingly similar to Earth's, and traces of water vapor exist. In 2020, researchers announced they had detected phosphine gas in the planet's atmosphere, a molecule that on Earth is often linked to biological processes. The finding was controversial and quickly challenged, but it reignited the debate over whether microbial life could survive in Venus's acidic clouds. Even if it proves to be a false lead, it shows how little we truly know about our nearest planetary neighbor, and how easily it can surprise us. Venus forces us to rethink what Earth-like really means. On paper, its size and composition are almost a perfect match, which makes its radically different fate even more dramatic. Planetary evolution isn't just about where a world begins, it's about the path it takes afterward and how sensitive that journey is to small initial differences. A few million kilometers closer to the Sun, a slightly altered atmosphere, a different volcanic history, any one of these could tip a planet's climate toward a point of no return. In the gallery of failed worlds, Venus is the one that had the resources to thrive, but turned them into a trap. Its dense atmosphere locks in heat. That heat fuels volcanic activity, and those eruptions release more gases that keep the atmosphere heavy and hot. It's a self-sustaining cycle, but one that sustains only its own hostility. If Mars is a frozen tomb, Venus is a burning prison. And yet, despite its extremes, Venus is vital to our understanding of what makes a planet livable and what can end that livability. It shows us the razor-thin line between success and collapse, and how even small differences in position or makeup can reshape a world's fate over geologic time. It also reminds us that planets are never static. They change, sometimes toward conditions that nurture life, and sometimes toward conditions that end it. Seen together, Mars and Venus are two different cautionary tales with the same ending, a surface where life, if it ever existed, is gone, and they are far from unique. Across our solar system and almost certainly across the galaxy, countless other worlds have followed similar paths. Some froze, some burned, some teetered for ages in a marginal state before tipping over the edge. Our next stop in this journey through failed worlds takes us to some of the most intriguing bodies in the solar system, places that may never have been fully habitable on their surfaces, but that could still harbor life in hidden, shielded environments. When we imagine where life might exist, our first instinct is usually to think of planets. That's natural. Earth is a planet, and it's our only confirmed example of a living world. But in our own solar system, some of the most promising candidates aren't planets at all. They're moons, not the inert, airless rocks you might picture, but worlds with oceans, ice, atmospheres, and in some cases chemical ingredients that hint at biology. These moons never had sprawling continents or blue seas reflecting sunlight. They've always lived under extremes, buried in ice, wrapped in thick haze, or locked in deep cold far from the sun. On the surface, they look lifeless. But below, in well-protected environments shielded from deadly radiation and temperature swings, there may be, or may once have been, the right conditions for life. They're what you could call almost worlds, bodies that didn't quite make it as surface habitats, but still hold remarkable potential beneath their exteriors. Europa, one of Jupiter's largest moons, is a prime example. At first glance, it's an icy wasteland, a gleaming surface scored with dark cracks and ridges where the ice has fractured and shifted. The scarcity of impact craters suggests the surface is young, constantly being reshaped. But Europa's true wonder lies beneath a vast global ocean, kept liquid by the heat generated through tidal flexing. As Europa orbits Jupiter, the giant planet's gravity stretches and squeezes it, generating friction deep inside. That friction produces heat, preventing the ocean from freezing solid. By most estimates, Europa's hidden sea holds more than twice the volume of all Earth's oceans combined. And where there's liquid water, there's potential for life. Europa's ocean likely interacts with its rocky seafloor, creating chemical energy sources. On Earth, similar conditions at deep-sea hydrothermal vents support rich ecosystems that thrive without sunlight, living entirely on chemical reactions. If anything like that exists on Europa, it would be one of the most promising environments for extraterrestrial life in our solar system. Enceladus, a small moon of Saturn, tells a different but equally captivating story. For years, Enceladus was thought to be just another frozen satellite, until the Cassini spacecraft revealed it was anything but ordinary. From cracks near its south pole, immense geysers erupt, flinging plumes of water vapor and ice particles hundreds of kilometers into space. These aren't just pretty fountains. Cassini's instruments detected salts, organic molecules, and other chemicals linked to the kind of water-rock interactions that on Earth are often tied to life. Like Europa, Enceladus is believed to hide a vast ocean beneath its icy crust, kept liquid by tidal heating from the immense gravitational pull of Saturn. The fact that this ocean vents directly into space makes Enceladus one of the most accessible places in the solar system to look for life. Instead of drilling through kilometers of ice, we could simply send a spacecraft to fly through the plumes and sample them. Then there's Titan, Saturn's largest moon, and the only moon in the solar system with a thick, planet-like atmosphere. Its surface is bitterly cold, about 179 degrees Celsius, yet it's home to lakes, rivers, and rainfall, not of water but of liquid methane and ethane. Titan's nitrogen-rich atmosphere also contains complex organic molecules, the building blocks of life. While it's far too cold for liquid water to exist on the surface, models suggest a hidden ocean of water mixed with ammonia may lie beneath its icy shell. Titan's intrigue goes beyond water-based life. If life there uses methane instead of water as a solvent, it would completely redefine what's possible for biology. And Titan isn't alone in this hidden ocean category. Other moons like Jupiter's Ganymede and Callisto or Neptune's Triton may also hold vast seas beneath their frozen crusts. On the surface, these worlds appear lifeless, but they remind us that surface conditions don't tell the whole story. A body can be deadly above while harboring something entirely different below. What makes them distinct from the failed planets we've talked about is that they never followed the same path as Earth. They weren't stripped of habitability. They never had it on the surface to begin with. Instead, whatever potential they hold has always been hidden, shielded deep inside. If life exists there, it would prove that even worlds far from the sun, circling giant planets rather than stars, can join the ranks of the living. But proof won't come easy. Europa's ocean is buried under tens of kilometers of ice. Enceladus's plumes are tantalizing but rare, requiring perfectly timed flybys to catch. Titan's surface is cloaked in thick haze, and its internal ocean is even harder to reach. Still, our tools are improving. NASA's Europa Clipper mission, set to launch in the coming years, will make dozens of close passes over Europa, mapping its surface and hunting for signs of activity that connect its ocean to the surface. Other mission concepts aim to revisit Enceladus to directly sample its plumes, or to land on Titan and study its strange chemistry up close. The stakes go far beyond finding life. These missions could reveal just how common the building blocks for life really are, and how many radically different environments might sustain it. If even one of these moons turns out to be alive, whether it's microbes, complex chemistry, or something entirely new, it would prove that life isn't limited to Earth-like planets in the habitable zone. That would make the galaxy feel far more alive, and it would expand how we think about the so-called graveyard of worlds. Because if life can exist in a place like Europa's dark ocean or Titan's methane lakes, then a world that looks dead from the outside might still be thriving inside. At the same time, their almost status is a reminder of fragility. If Europa's ice had been thicker, its ocean might have frozen long ago. If Enceladus didn't vent its ocean into space, we might never know it existed. If Titan lacked its unusual atmosphere, it might be just another anonymous ice ball. These moons walk a delicate line, and whatever habitability they have could be lost if that balance shifts. In the bigger picture of whether Earth is just one survivor among many failed worlds, these moons are a vital clue. They show that habitability isn't black and white. To show that habitability isn't black and white, a world can exist in the grey space between alive and dead, where the surface tells one story and the interior tells another. And they also hint at a sobering truth. If life can arise in these hidden places, it can also vanish without a trace, dying silently in the dark without ever leaving a visible mark. From here, our search for failed worlds takes us beyond the sun's reach, into the realm of probability and scale, to the idea that Earth may be just one of countless attempts the universe has made at producing a world like ours. And in that grand experiment, most will not last. Looking just at our solar system, we already see a spectrum of outcomes. Earth teeming with life in all its complexity. Mars, which may have once been warm and wet, now frozen and dry. Venus, which could have had oceans, now a furnace cloaked in acid clouds. The icy moons, some with oceans still full of promise, others locked in silence, all of them orbiting the same star, born from the same swirling cloud of dust and gas, yet each ending in a completely different state. This variety drives home a simple but profound point. The conditions that make a planet livable are not just rare, they're the result of layer upon layer of chance. Think of the birth of a solar system as an unending series of lucky draws, the composition of the original gas and dust, the exact distances of planets from their star, the timing and severity of impacts, the tilt of a planet's axis, the strength of its magnetic field, the mix of greenhouse gases, the size of its moons, the stability of its neighbors. Each factor shapes a world's destiny. Change any one of them enough, and the outcome changes too. Earth's position in the solar system keeps it in that sweet spot where liquid water can exist on the surface. Our atmosphere is just right, thick enough to hold onto that water, but not so heavy that it traps overwhelming heat. Our magnetic field acts as a shield, deflecting harmful solar and cosmic radiation. Our large moon helps keep Earth's tilt stable, preventing wild swings in climate. Plate tectonics constantly recycle carbon dioxide, helping regulate the planet's temperature over millions of years. Even asteroid impacts, as destructive as they can be, played a part, delivering water and organic molecules without striking often enough to wipe life out completely. But none of this was inevitable. Push Earth a little closer to the sun, and we might have ended up like Venus. Move it slightly farther away, and we could have frozen into a Mars-like wasteland. Without the moon, Earth's tilt might have wobbled wildly, throwing our climate into chaos. Without a magnetic field, the solar wind could have stripped away our atmosphere. Without plate tectonics, carbon dioxide could have either built up to Venus-like levels or been locked away in the crust, sending us into a permanent snowball state. Now, Scale that idea up to the galaxy. Hundreds of billions of stars, each with their own planetary systems. Many of those planets may start with some of the ingredients for life, but the odds of landing the exact right combination and keeping it for billions of years are incredibly small. Even if life sparks somewhere, the same hazards that threaten Earth could push it toward failure. In other words, winning the planetary lottery once isn't enough. You have to keep winning draw after draw for as long as life needs to survive. This shifts how we think about habitability. It's not just about being in the habitable zone, the orbital range where temperatures allow liquid water. That's only the first ticket in the cosmic lottery. The rest of the winning numbers come over time, in the form of stability, the ability to stay in that narrow life-friendly zone for billions of years. Our own solar system offers a warning. Many worlds may start in good positions but drift out of them. Some changes are subtle, like a star's gradual brightening. Others are violent, massive impacts, volcanic upheavals or gravitational disruptions. And that's why the galaxy is likely full of failed worlds. For every planet that stays stable for billions of years, dozens may have come close but lost their habitability too soon. Some, like Venus, probably failed early, heating into unlivable greenhouses before life could even take hold. Others, like Mars, may have failed late, losing their atmosphere after a long stretch of potential. The result? A galaxy of incomplete stories, beginnings without middles, middles without endings. There's another twist, the role of pure chance. Even with perfect conditions, random events can flip a planet's fate. On Earth, the asteroid impact that ended the dinosaurs could have been larger or struck in a worse location, wiping life out entirely. A nearby supernova could have bathed us in lethal radiation, stripping our ozone layer. A volcanic eruption at the wrong time could have triggered a runaway climate shift. These are the bad draws in the cosmic lottery, the ones you can't predict. Earth's survival so far has come from both resilience and luck. Our systems can absorb some disruptions, but not all, and over billions of years avoiding the disasters that could overwhelm them has taken a certain amount of fortune. You can stack the odds in your favor, but you can't control every draw. When we search for life beyond Earth, we're essentially searching for other jackpot winners. But even winners don't keep their streak forever. But stars age, planets evolve, conditions shift. The real question isn't just whether life exists somewhere else right now, it's whether it can last. The graveyard of planets we've imagined is probably filled with worlds that won the early rounds, only to lose later. And that comes with a humbling implication. If we do find life elsewhere, it's probably temporary, just like ours. Even the most stable planet we discover today has no guarantee of staying that way forever. The cosmic lottery never stops. Every planet is playing whether it wants to or not, and sooner or later the odds catch up. That doesn't mean life is doomed everywhere, but it does mean that permanence is rare. It's tempting to believe that intelligence, technology, and advanced civilizations can tilt the odds, protecting a world from the same fates that claimed others. And maybe, to some extent, that's true. We might learn to control our climate, deflect dangerous asteroids, or even move our civilization to new worlds. But those are responses to the dangers we already understand. The universe also holds threats we haven't imagined, and history shows nature has a talent for surprise. For now, Earth is holding a winning ticket. We're in the right place with the right balance of conditions at the right moment. But the more we study our solar system and the worlds beyond it, the more we realize just how fragile that position really is. We are not the inevitable product of planetary evolution. We are the result of an improbable sequence of events, any one of which could have gone differently. And as we search for life elsewhere, we need to remember the cosmic lottery doesn't just decide who gets a shot at life. It also decides how long that shot lasts. Even the luckiest planets can eventually find themselves in the graveyard. From here, the conversation moves beyond chance and into survival, into the concept known as the Great Filter. It's the idea that somewhere along the journey from lifeless rock to a thriving, spacefaring civilization, there are obstacles so difficult that almost no one makes it past them. In other words, there may be steps in the evolution of life that are not just improbable, but nearly impossible. These bottlenecks could explain why, in a galaxy overflowing with planets, we see no clear evidence of anyone else. The Great Filter is often brought up in discussions of the Fermi paradox, the puzzle of why, Given the age and size of the galaxy, intelligent life isn't everywhere we look. There are hundreds of billions of stars, billions of planets in habitable zones, and countless opportunities for life to emerge. Yet, the skies are quiet. One possible answer, somewhere along the chain of steps from chemistry to civilization, the odds drop so low that most worlds stall out. Maybe the great filter sits at the very beginning. Perhaps the origin of life, abiogenesis, is so rare it only happens once in a trillion tries. If that's true, most habitable planets would remain barren forever. They might have oceans, atmospheres, and stable climates, but never take that leap into biology. In that case, Earth is extraordinary because we crossed the first and hardest barrier. But the great filter could also lie later. Maybe life starts easily and evolves into complex organisms fairly often, but then stumbles. Planets could be undone by climate instability, mass extinctions, or asteroid impacts before intelligence has a chance to develop. Or intelligence could arise, but civilizations might collapse before they spread beyond their homeworlds, brought down by war, environmental collapse, or their own technology. Then there's the most unsettling possibility of all. The great filter is still ahead of us. If that's the case, the galaxy's silence isn't proof we're alone. It's a warning. Every advanced society might eventually hit the same insurmountable challenge. It could be something obvious, like managing technology without destroying ourselves, or something subtle, like slow planetary changes that erode habitability beyond repair. If this is our future, then the quiet of the cosmos is the sound of civilizations that didn't make it. The failed worlds of our own solar system offer clues. Mars shows how a habitable planet can lose its atmosphere and water. Venus shows how a climate can spiral into runaway heat. The icy moons remind us that habitability can remain locked away, never developing into surface life at all. None of these worlds ever made it through the full sequence toward complex technological life. On Earth, life began quickly after the planet cooled, which suggests the first step, abiogenesis, might not be the hardest one. But for nearly 3 billion years, it stayed microscopic. Complex, multicellular organisms didn't appear until about 600 million years ago, and humans have only existed for the briefest sliver of that time. That points to a possible bottleneck, the leap from simple life to complex life. If that transition is truly difficult, then the galaxy may be full of living planets, stuck forever at the microbial stage. And then there's the question of survival. Human civilization is less than 10,000 years old, a blink on a geological timescale. In that short time, we've created technologies capable of changing the planet's climate, splitting atoms and exploring the solar system. But we've also brushed close to self-destruction more than once. Our systems are powerful but fragile, and it's not hard to imagine how a string of bad decisions or plain bad luck could end the experiment. If other civilizations face the same vulnerabilities, that might be why none have lasted long enough to fill the galaxy. The great filter may not be one single disaster. It could be a collection of challenges, environmental, technological, social, that when combined are almost impossible to overcome. A planet might survive asteroid strikes, but fail to keep its climate in balance. A species might evolve intelligence yet never master cooperation on the scale needed to manage its world's resources. A civilization might harness immense technology and still lack the foresight to avoid destroying itself. The result is the same: another world joins the silent majority in the graveyard of planets. It sounds grim, but the great filter is still just a hypothesis. We don't know where it sits, how strong it is, or whether it's the same everywhere. Earth may have already passed the hardest barrier, making us one of the rare survivors. Or our real test could still lie ahead, and our fate will depend on recognizing dangers that others never survived. Either way, the idea forces us to see life's journey for what it is, not a steady climb toward progress, but a fragile ascent past cliffs, ledges, and sudden drop-offs. Every success story exists only because it dodged countless chances to fail, and in the galaxy's grand scale, success may be the exception, not the rule. Seen in this light, Earth's survival isn't just about holding on to habitability. It's about actively steering through the hazards that have ended other worlds. Whether the great filter is behind us or ahead, the graveyard of planets reminds us the universe doesn't promise permanence. It offers conditions, and we must fight to keep them. That means looking hard at what we're doing now, the risks we face, the moves we're making to avoid disaster, or the mistakes that could push us toward it. If the other worlds in our solar system have taught us anything, it's this habitability is never permanent. Even when all the right factors align and life begins, there's no guarantee it will stay. Planets and moons are restless things. Surfaces, skies, and interiors change, sometimes slowly, sometimes abruptly, and those changes can tip the balance faster than life can adapt. It's one thing for a planet to never cross the threshold into habitability. It's another for it to get there, nurture life, and then lose it. Those are the stories that reveal just how fragile the process truly is. We don't yet have a confirmed example of a once-living planet that is now entirely dead, but Mars may be the closest candidate. The dried riverbeds, the ancient lake beds, the evidence of long-vanished seas all suggest that billions of years ago it could have been a cradle for microbes. If life ever took root there, it didn't last. A fading magnetic field, a thinning atmosphere, and a changing climate would have driven surface life into crisis. Perhaps some adapted underground, perhaps others froze into eternal dormancy, but any thriving surface ecosystem was erased. And that story could have played out countless times across the galaxy. Imagine a planet orbiting quietly in the habitable zone, seas glittering under its sun, green coasts under breathable skies. Microbes emerge, then slowly evolve into more complex life. Then something shifts. The star grows more active, unleashing radiation that strips the air away, or the planet's internal heat fades, shutting down the volcanic activity that replenishes its atmosphere, or a colossal impact tilts its axis, trapping it in wild, irreversible climate swings. In any case, the ecosystem collapses. From a distance, the planet still looks promising, still in the right place, but up close, the surface is barren. Life may be quick to begin, as it was on Earth, but if starting is easy and staying is hard, then the universe could be full of worlds with beginnings but no endings, planets littered with fossils and empty landscapes. Some of these worlds might even trick us. For a time, their atmospheres could hold the chemical fingerprints of life, oxygen, methane, or other gases, even after the biosphere is gone. But those traces fade as the air drifts back toward chemical equilibrium. From afar, we might celebrate such a world as a living twin, only to find it's an abandoned building with the lights still on. The reasons life's story can be cut short are as varied as the stars themselves. Orbits can shift, nudging a climate out of balance. Geological cycles can choke a planet in greenhouse gases or strip them away. Magnetic fields can die, letting lethal radiation pour in. Impacts can sterilize entire worlds. Sometimes, the change comes from life itself. Billions of years ago on Earth, the rise of photosynthesis filled the atmosphere with oxygen, a blessing to us today, but poison to much of the life that existed then, triggering one of our earliest mass extinctions. And when intelligent life enters the picture, the risks multiply. Civilizations can destabilize their own climates, strip their resources, or unleash technologies they can't control. In those cases, life isn't just reacting to environmental change, it's causing it. Humans have only had that power for a short time, yet the impact has been enough to make us question how long our good fortune will last. That's what makes the idea of life that begins but doesn't last so haunting. When it ends, it doesn't go out with a cosmic announcement, it just goes quiet. And silence is the most chilling sound in the universe. A planet that loses its biosphere rarely leaves a bold sign for passing civilizations. There's no flashing beacon, no universal obituary. Its history gets buried in the rocks, isotope ratios locked in ancient sediments, fossilized cells hidden in mineral veins, chemical fingerprints etched into weathered layers. To notice, you'd have to go there or send a probe close enough to read the planet's scars. It's entirely possible the galaxy is full of these quiet ruins of ancient life, invisible to anyone who isn't looking closely enough. And it's possible our own world has brushed against that fate more than once. Earth's history is punctuated by mass extinctions, moments when the majority of life was wiped away. Each time it rebounded, but there's no law that says it had to. A slightly larger asteroid, a longer ice age, or a more extreme volcanic eruption, and the rebound might never have come. In that alternate history, Earth would be just another silent rock with only geological whispers to tell anyone we were ever here. The lesson is simple and sobering. Being alive is not the same as being safe. Life adapts, but it's not invincible. Even the most perfect conditions are temporary if the underlying systems drift out of balance. For scientists searching the stars, that's a warning. We might see signs of life in the spectrum of a distant planet's atmosphere, only to find the biosphere is already gone. We might land on a world that once teemed with microbes, only to find their remains locked in ice or stone. Both would still be monumental discoveries, proof that life exists elsewhere, or has existed, but they would also underline how rare it is to find a world still in the middle of its story. Right now, Earth is in that rare window, a stretch of time when the conditions for life and the life to use them actually overlap. We don't know how long it will last, but we do know it won't last forever unless we make it last by protecting the systems that keep us stable, preparing for changes we can't stop, and understanding that the universe's default state is not life, but absence. Some threats creep in slowly: climate shifts, gradual atmospheric changes, the slow brightening of a star, giving life time to adapt. Others arrive like a hammer, sudden, massive, and final. These are planetary extinction events, disasters powerful enough to erase millions of years of progress in moments. On Earth, we've had close calls, and we've taken direct hits. The fossil record is marked by mass extinctions, times when vast swaths of life vanished in geological instants. The causes vary: massive volcanic eruptions, asteroid strikes, shifts in ocean chemistry, global glaciations, even biological revolutions like the rise of oxygen in the atmosphere. After each, Earth was a different planet. New survivors, new ecosystems, new rules. The most famous example came 66 million years ago, when an asteroid roughly 10 kilometers across slammed into what is now the Yucatan Peninsula. It unleashed more energy than billions of nuclear bombs, shattering everything in its immediate path. But the real catastrophe came after dust and vapor choking the skies, sunlight blocked for months or years, global temperatures plummeting, photosynthesis grinding to a halt, food chains collapsing, 75% of all species vanished. This isn't unique to Earth. Any planet with a thin enough atmosphere for big impacts is at risk. The scars are all over our solar system. The Moon, Mars, Mercury, even the icy moons are pocked with craters, each a record of an ancient collision. In a young planetary system, the danger is even worse, with leftover debris from planet formation sweeping through space like cosmic shrapnel. Volcanism can be just as deadly. Around 252 million years ago, the Siberian Traps eruptions poured greenhouse gases into Earth's air for hundreds of thousands of years. The result? The deadliest known extinction, 90% of marine life gone, 70% of land species wiped out, a planet choked by heat and acid oceans, a world with more volcanic activity than ours, or no way to pull excess carbon back from its skies, could plunge into a runaway greenhouse forever. Then there's the universe itself, unpredictable and merciless. A nearby supernova, a gamma-ray burst, or an extreme solar flare can flood a planet's surface with lethal radiation. These blasts can strip away atmospheres, shatter ozone layers, and trigger extinction cascades. And unlike with asteroids or volcanoes, there's no shield a planet can raise against that kind of cosmic fire. Even ice can be an executioner. Snowball Earth events when the planet freezes over almost entirely may have happened more than once here. Some life can cling to isolated pockets under the ice, but the available habitat shrinks to almost nothing. Whether life recovers depends entirely on whether the planet can thaw again. On a world without strong internal heat, or the right atmospheric chemistry, that thaw might never come. In all of these scenarios, the end comes not with a bang alone, but with silence. A living world turns quiet, and stays that way. Biology itself can be the spark for planetary-scale catastrophe. On Earth, the Great Oxidation Event 2.4 billion years ago began with cyanobacteria, tiny architects of photosynthesis, releasing oxygen into the air. At the time, oxygen was poison to most life. Its rise transformed the atmosphere, collapsing ecosystems in a mass die-off. Eventually, life adapted. But there's no guarantee a similar shift elsewhere would end in balance. A change in atmospheric chemistry can just as easily push a planet into a new, permanent and hostile state. And extinction doesn't have to mean sterilization. If a catastrophe reduces life to only its simplest forms, wiping out the complexity that took billions of years to evolve, the clock resets, and not every world gets the time or the luck to climb back up. From light years away, you might never notice the difference. A planet that lost its forests, reefs, and megafauna in a volcanic apocalypse could still look almost identical to one bursting with life. Oceans would still glint in the star's light. The air could still hold familiar gases. The orbit would be the same. Only on the surface would the truth be obvious. A biosphere hollowed out, its intricate balance broken. That means some of the promising worlds we find in the galaxy may already be ghosts. We'd be looking at the aftermath without realizing it. The quiet between what was and what will never be again. This could be one reason the galaxy feels so silent. The survivors of extinction are invisible from our vantage point, and the truly dead worlds even more so. For Earth, our own extinction record is a reminder that stability is borrowed, not owned. The same forces that shaped us still exist. New ones will emerge. We can't prevent every disaster, but we can prepare by tracking asteroids, mapping volcanic activity, monitoring the sun, and building the tools to respond before catastrophe strikes. But there's one category of extinction event unique to certain worlds, the kind that doesn't come from the outside at all. It comes from within. Sometimes the force that ends a planet's stability is the very life it nurtured. A civilization can be both the peak of evolution's long climb and the reason that climb ends abruptly. It doesn't take an asteroid to end an age. Sometimes it takes nothing more than the right mix of complexity, ambition, and error. Human civilization is young, a few thousand years since the first cities, a few centuries since industrialization, a few decades since our technology became capable of changing climate and atmosphere on a planetary scale. In that blink of geological time, we've achieved extraordinary things, from medicine to spaceflight, but also created risks no other species in our history has faced. We can now alter the very systems that keep us alive faster than those systems can recover. History is full of fallen civilizations. The Mayan cities, the Indus Valley, the Roman Empire, Easter Island. Their causes varied: environmental collapse, depleted resources, political instability, war, disease, economic failure. But they shared a pattern. The complexity that once gave them power became a weakness when conditions shifted. The difference now is scale. Ancient collapses were local. The fall of one empire didn't end human life everywhere. Today our networks for food, energy, transport, communication span the globe. That makes them powerful and fragile. A failure in one part can ripple across the whole system. Environmental strain is a common thread, and it's global now. Overuse of resources, deforestation, water scarcity, degraded soils, all amplified by a changing climate that alters weather, shifts agriculture, and makes extreme events more common. The speed of these changes is as dangerous as their scale. Conflict adds another layer. In the past, war devastated regions. Now it could disrupt or even end global stability. We possess weapons that could erase much of the biosphere outright, or poison it beyond repair. And not all threats are deliberate. Technological accidents, failures in power grids, communications, biosafety, or critical infrastructure can cascade into disasters far beyond their point of origin. In a world where these systems are tied to food, water, and healthcare, such failures can spread shockwaves through the entire civilization. Even economics can become a trigger. A society built on constant growth can collapse when the growth stops, and in a globalized system, a crisis in one sector or region can trigger instability everywhere. Disruptions in trade, shortages of critical resources, or a collapse in trust toward institutions can set off a dangerous feedback loop. Once cooperation frays, the intricate systems that depend on coordination begin to unravel. Diseases have played their part in history's collapses, and in our connected age, outbreaks can spread across continents in days. Medical science has advanced, but there's no guarantee of safety. New pathogens can emerge, existing ones can evolve resistance, and even a temporary failure in health systems can ripple outward into crises that strain every other sector of society. What turns a societal collapse into a planetary collapse is when it pushes the biosphere beyond the point of recovery. A civilization can fall and be replaced if the environment remains stable enough to support the next one. But if the fall brings deforestation, soil exhaustion, mass extinctions, or climate disruption, the damage lingers. The planet itself becomes less able to host future civilizations, edging it closer to the silent graveyard of failed worlds. From a broader view, civilizations are experiments, attempts to organize intelligence, resources, and energy on a scale far beyond any individual or small community. Success means balancing ambition with restraint, growth with sustainability, and innovation with foresight. Tip too far in the wrong direction, and collapse becomes likely. If that collapse happens after the biosphere has been degraded, there may be no second act. It's not hard to imagine that if intelligent life exists elsewhere, it faces the same pressures: finite resources, environmental shifts, internal conflicts, and the temptation to advance technology faster than the ability to control it. Fail that test and the civilization may vanish, leaving behind a world that still orbits its star but no longer supports complex life. From far away, time and weather erase the traces until it looks as though nothing ever happened. Which leads back to the question at the heart of this search. If Earth is just one attempt at a living, thinking world, how many others have reached this point, only to fall? If the answer is many, then maybe the silence we hear isn't from worlds that never lived, but from worlds that lived, advanced, and then died. But not every collapse comes from within. A planet's survival is also at the mercy of the star it orbits. No matter how carefully it manages its resources or how well it maintains stability, it still lives under the long shadow of its sun. If Earth teaches us anything, it's that survival has been a mix of resilience and sheer luck. Our history is full of near misses, events that could have ended the story long before humans ever arrived. Without those breaks falling in our favor, we'd be nothing more than another silent rock in the cosmic graveyard. Some of those escapes happened when life was still microscopic. Billions of years ago, the sun shone far dimmer than it does today, faint enough that by logic alone, Earth should have been frozen solid. Yet somehow, greenhouse gases and geological activity trapped enough heat to keep water liquid. Fail that balance, and life might never have started. Impacts, too, have shaped our odds. The early solar system was a shooting gallery, with asteroids and comets striking regularly. One colossal impact created our moon before life began, but had it happened later, it might have sterilized the planet. Even after the bombardment slowed, danger remained. The asteroid that ended the dinosaurs was large enough to destroy much of Earth's life, but not large enough to finish the job. A slightly different size or strike location could have left nothing to recover. Volcanoes have nearly done the same. The Siberian Trap's eruptions 252 million years ago caused the deadliest extinction in Earth's history, wiping out around 90% of marine life. We recovered only because the planet's climate eventually restabilized, something Venus never managed. Ice ages, too, have tested us. Around 700 million years ago, snowball Earth events froze the planet from poles to equator. Life survived only in hidden refuges, perhaps in deep-sea vents or under thin ice where sunlight could still reach. Without those pockets, global photosynthesis might have collapsed forever. Even our moon and magnetic field have been silent guardians. The moon's gravitational pull keeps Earth's tilt stable, avoiding wild climate swings like those Mars has endured. The magnetic field, powered by molten iron in the core, shields us from the solar wind that stripped Mars of its air and water. Both have been constant safeguards for billions of years. And then there's biology itself, capable of almost ending the experiment from within. The Great Oxidation Event, driven by photosynthetic microbes, poisoned much of the existing life. Earth adapted, but the outcome could easily have been extinction. That life not only survived the Great Oxidation Event, but eventually adapted to oxygen was another improbable break, one that unlocked the kind of energy-rich metabolism complex organisms depend on today. Humanity has had its own brushes with catastrophe, though most are hidden in the deep past. The Toba supereruption around 74,000 years ago may have shrunk the human population to a sliver of its former size. Ice Age swings, forced migrations, and genetic bottlenecks that could easily have gone another way if the cold had been just a little harsher or longer. Even in recorded history, outbreaks of disease, waves of famine, and large-scale conflict have threatened vast populations, though never yet on a truly species-ending scale. Threaded through all of it is the same pattern. Survival often comes down to a mixture of forces we can't control, and the few we can. Geological processes, orbital mechanics, and stellar whims play out far beyond human influence. But how life responds, by adapting, finding refuges, or reshaping its environment, determines whether a close call becomes the final chapter. That's what makes Earth's string of narrow escapes so striking. Every one of them could have gone the other way. A slightly different asteroid trajectory, a few more centuries of volcanic gas in the sky, a marginally weaker magnetic field. Any of these could have rewritten the story entirely. In planetary history, small changes can separate a biosphere that thrives for billions of years from one that ends abruptly. From the perspective of the graveyard of worlds, these escapes are rare. Most planets don't manage them. Some take a single blow they never recover from. Others endure a slow barrage of smaller hits that erode habitability over time until there's nothing left to save. Earth's continued stability doesn't guarantee future safety, but it does mean we've been granted an opportunity most worlds never see. That opportunity is also a warning. Narrow escapes are nature's way of telling us that stability rests on contingencies and coincidences. Ignore that, and we risk joining the silent majority. We can't prevent every threat, but we can prepare for some, and the more we learn from the fates of other worlds, the better we can see where preparation matters most. The truth is, Earth's journey from formation to now has never been a clean, predictable arc. It's been a twisting path shaped by sudden turns, improbable recoveries, and moments when things could just as easily have broken the other way. That's the role of chance, the unforecastable role of the cosmic dice. And alongside it is chaos, in the mathematical sense, tiny variations in initial conditions that over time yield vastly different outcomes. Chance is easy to picture. It's whether an asteroid misses or strikes, whether a planet forms with just enough molten iron in its core to sustain a magnetic field for billions of years, or cools too fast and loses its shield, whether plate tectonics begin early enough to regulate the climate, or the crust locks up too soon and lets the atmosphere spiral out of balance. These are coin flips on a planetary scale, and a world's long-term habitability depends on how often they land the right way. Chaos is subtler. It's not about one-off events, but about sensitive systems where small shifts create cascading changes. A planet's orbit, for instance, is nudged constantly by the gravity of its neighbors. Over millions of years, those nudges can alter its climate, its seasons, or even its place in the habitable zone. Climate itself is a chaotic system. A tiny tweak in atmospheric chemistry, ocean currents, or solar output can tip it into an entirely new and potentially irreversible state. On Earth, the interplay of chance and chaos has been relentless. The dinosaur-ending asteroid could have missed by a few thousand kilometers. The Toba eruption might have coincided with other environmental stresses, sealing our fate. The faint young sun paradox could have gone unsolved if volcanic activity had been just slightly weaker, leaving Earth frozen for eons. In each case, small variations rippled outward, changing everything. Mars likely lost its magnetic field early, letting the solar winds strip away its air and water. That may have been the inevitable result of its smaller size, its cooling rate, or subtle differences in its early chemistry, all shaped by random collisions during formation. Venus may have started with conditions not far from Earth's, but tiny differences in rotation, sunlight, or volcanic outgassing set it on a path toward runaway heat. Both worlds show how small early divergences can have enormous final consequences. This is why habitable zone is such an oversimplification. A planet can sit squarely in it and still be a dead rock if chance and chaos align against it. Conversely, some worlds may survive outside the textbook zone thanks to thick atmospheres or internal heating. What matters most is the trajectory, and that trajectory is hypersensitive to initial conditions. When scientists model planetary evolution, they run simulations thousands of times with only minuscule changes in the starting setup. The results diverge wildly. That's chaos, and in the real universe, there's no reset button. A planet gets one run, drift toward uninhabitability, and there may be no way back. For life, stability isn't just about being in the right place at the right time, it's about navigating the unpredictable twists along the way, adapting to extremes, rebounding after disaster, and seizing opportunities whenever they appear. Even flexibility has its limits. There are thresholds past which adaptation simply isn't possible, and those thresholds can be crossed in an instant if chance and chaos align in the wrong way. In the silent cemetery of lifeless worlds, these forces are the unseen sculptors, shaping which planets turn promising beginnings into lasting success, and which ones end in failure. They're also the reason exact Earth twins are unlikely. Even if two planets start out nearly identical, their paths will split over time, shaped by random asteroid strikes, subtle orbital changes, and the self-reinforcing loops in their climate and geology. Fast forward a few billion years, and their surfaces might have nothing in common. That unpredictability makes our search for life harder. We can spot worlds in the so-called habitable zone, measure their size and orbits, even sniff their atmospheres for hints of biology, but we can't know their full backstory without being there. A planet might look perfect from light years away, only for a closer visit to reveal it suffered a slow collapse or a sudden mass extinction centuries ago. The evidence could be faint, buried under dust, ice, or volcanic ash. Chance and chaos can also work in life's favor in ways we haven't yet imagined. A destructive asteroid might wipe out one ecosystem but create conditions for another to flourish. A gentle wobble in a planet's orbit might drive seasonal shifts that boost biodiversity. Even catastrophes can at times open new evolutionary doors, as they have on Earth. These same forces that can wipe life out can also toughen it, shaping it into something more resilient. Whether the outcome is destruction or renewal depends on a shifting balance that no one can perfectly predict. And no matter how stable a planet seems, none are immune to these forces. Civilizations face the same reality. We can plan, build safety nets, and try to forecast threats, but randomness is always part of the equation. The best we can do is prepare for a range of scenarios, knowing that the real one might be something we never saw coming. Seen in the bigger picture, this only underscores how rare and fragile long-term habitability really is. Most planets will never get the mix of lucky breaks and survivable challenges that Earth has had so far. And even here, the story isn't finished. The next card we draw could be a harmless fluctuation, or the first link in a chain of events that transforms our world completely. From here, it's natural to turn the question toward our own search for life. How do we tell the difference between a thriving planet and one that's running on the fading echoes of its past? And how might we spot those rare worlds that defied the odds in ways we've never seen before? The universe, it seems, dislikes waste. Matter, energy, and even the ingredients of life are constantly used, broken down, and reassembled into something new. Stars die, but their ashes seed the next generation of suns and planets. Planets are shattered, but their fragments may become moons or be swept into new worlds. Even the bodies of living things are dismantled molecule by molecule, long after the creatures themselves are gone. On a cosmic scale, the universe is the ultimate recycling system. For planets, this process is baked in from the very beginning. The iron in Earth's core, the silicon in its crust, the carbon in its air and in our bodies, all of it was forged inside older stars. Some of those stars died quietly, drifting their outer layers into space. Others died violently as supernovae, flinging their contents across light years. Over millions of years, gravity gathered these scattered elements into new systems. Our Sun is one of those second-generation stars, and Earth itself is built from the debris of ancient worlds that no longer exist. Every planet, moon, and asteroid is in essence made of cosmic leftovers, and the recycling doesn't stop once they form. Geological activity is constantly reshaping a planet's surface, erasing the old and making way for the new. Mountains are worn down to sediment, only to be lifted skyward again. Volcanoes bring up material from deep within, where it weathers into soil. Even the atmosphere is part of this cycle. Datases move in and out through processes like volcanism, respiration, and photosynthesis. On Earth, this recycling is one of the keys to habitability. The carbon cycle, for instance, helps regulate global temperature over immense spans of time. Without it, Earth could have locked into a permanent ice age or spiraled into a Venus-like greenhouse. Life adds another layer to the recycling system. Organisms don't just adapt, they reshape their surroundings. Plants take in carbon dioxide and release oxygen. Animals reverse the exchange. Decomposers break down the dead, returning nutrients to soil and water. Over time, biological processes weave themselves into geological ones, creating a feedback loop where life helps sustain the planet, and the planet sustains life. But recycling isn't always slow and gentle. Sometimes it's jump-started by disaster. An asteroid impact can vaporize rock, throw debris into the air, and scatter material across the globe. A supervolcano can bury landscapes under lava, redirect rivers, and redraw coastlines. These events can erase ecosystems, but they can also create new environments for life to take hold. Land left bare by retreating glaciers, for example, starts as a wasteland and slowly fills with plants, animals, and entire communities. The same principle plays out far beyond individual planets. Across the galaxy, giant clouds of gas and dust, the nurseries of stars and worlds, are constantly replenished by the remains of older systems. The quiet winds from dying stars, the violent debris from supernovae, the steady outflow of matter from aging giants, all of it feeds these clouds. Over millions of years, gravity gathers the material, igniting new suns and giving birth to new planets. Every newborn world is in effect a blend of countless older ones. Even black holes, which seem like final endpoints, can shape galaxies by stirring gas and triggering new waves of star formation. Even black holes, as final as they may seem, still feed the cosmic cycle. While the matter they consume is gone to us in its original form, their immense gravity, powerful radiation, and energetic jets can stir their surroundings in ways that spark the birth of new stars and structures. In this way, even the most extreme objects in the universe are part of creation's ongoing loop. From the graveyard of worlds, recycling means no ending is truly final. A planet that loses its habitability might be shattered by collisions, its fragments joining other worlds. Its atmosphere could be stripped away, its gases drifting into the interstellar medium to one day help build new planets. Even its water, frozen or vaporized, might eventually find its way elsewhere. The elements that once nurtured life can do so again, just not in the same place or the same form. For civilizations, this reality carries a humbling message. The metals in our devices were forged in ancient stars and passed through countless worlds before arriving here. The oxygen we breathe has cycled through living systems beyond measure. Even the hydrogen in the water we drink has existed since the first moments after the Big Bang. In the most literal sense, we and everything we make are built from recycled matter. This also means that when we search for life beyond Earth, we're not looking for rare or magical substances, just the familiar ingredients of carbon, oxygen, nitrogen, and a handful of other elements that have been part of the universe's toolkit for billions of years. What matters is how these pieces are arranged, and whether they end up in an environment that can hold them together long enough for life to take hold. Recycling continues even in the twilight of civilizations. When a society falls, its metals, ceramics, and plastics eventually break down and return to the planet's natural cycles, though often on vastly different timescales. In geological terms, the ruins of entire cities could be reduced to sediment in the blink of a planet's lifetime, their remnants pressed into rock layers waiting for some future explorer, if one ever comes, to uncover. Whether or not that happens, the material will still be absorbed into the ongoing transformation of the world. This dual nature of cosmic recycling is both comforting and cautionary. On one hand, nothing is truly lost. On the other, nothing stays as it is forever. Planets, civilizations, even stars, all are temporary configurations of matter and energy, destined to be dismantled and reused in ways that may bear no resemblance to their original purpose. Earth's current ability to support us is just a fleeting phase in a process that's been running for billions of years and will continue for billions more. The universe's recycling engine doesn't work for or against life. It simply runs. Whether life benefits depends entirely on timing and circumstance. A planet can form from recycled matter in a region perfectly suited for habitability, or in a place where such conditions never align. From our viewpoint, the process is indifferent. From the universe's perspective, it's simply how things work. This view makes our situation feel both delicate and deeply connected. We are links in a chain stretching back to the first atoms and part of a chain that will extend far into the future, long after we're gone. Our survival depends on the continuity of certain cycles, but it also depends on the reality that nothing in the cosmos remains unchanged. In that sense, every planet, living or dead, is part of the same endless transformation. If Earth is one of many worlds, whether successful or failed, then eventually its materials will feed into something else, another planet, another star, another potential cradle for life. From the graveyard's perspective, failure is never final, it's just another phase in the cycle. What truly matters is what happens while a world is still intact, still capable of sustaining the complexity we call life. And that leads to the next question: how do we use this understanding in our hunt for life beyond Earth? Knowing how worlds are created, destroyed, and renewed helps guide us, showing us where to look, what patterns to expect, and how to interpret the vast silence we so often hear in return. It's easy to picture the graveyard of worlds as a still, silent gallery of lost planets, their stories ended, but in reality, they are far from mute. Each scarred surface, each layered rock formation, each trapped bubble of ancient atmosphere is a page in a record written over billions of years. And those records are priceless. They may not give us every detail, but they reveal patterns, showing the pathways that lead to collapse and offering context for understanding our own fragile position in the cosmos. The first lesson they offer is that habitability is always in motion. Mars, with its dried riverbeds and minerals formed in water, proves that a planet can begin warm and wet, yet end up frozen and barren. Venus, with its crushing air and hellish heat, suggests it may once have been temperate before tipping into a runaway greenhouse. Neither planet stayed as it began, and in both cases the change moved away from habitability, not toward it. The second lesson is that just being in the habitable zone isn't enough. That's only the starting line. The real challenge is keeping conditions stable for the billions of years complex life requires. A small atmospheric change, a spike in volcanic activity, or the loss of a magnetic field can nudge a planet out of that delicate balance, sometimes permanently. The third lesson is that mass extinction is anything but rare. On Earth, we often talk about the Big Five extinctions, the most dramatic die-offs in our history. But the fossil record is filled with smaller, lesser-known events triggered by shifting seas, climate changes, or regional volcanic outbursts. If our planet, with all its apparent advantages, has faced so many resets, it's not hard to imagine countless other worlds enduring even more, some never recovering at all. Finally, the dead worlds remind us that catastrophe can strike fast or unfold slowly. An asteroid can destroy in seconds, but a gradual loss of atmosphere or a creeping climate shift can be equally fatal over time. A biosphere can wither over millions of years without any single dramatic tipping point. And that's critical for how we search for life elsewhere. A planet can look serene and stable from a distance, yet be quietly sliding toward its end. Without knowing how fast and in what direction those changes are happening, we might mistake a dying world for a permanent paradise. That's why the dead planets teach us a critical truth: resilience has limits. Life can adapt, but only to a point. Once certain thresholds are crossed, even the toughest organisms can't survive. If Mars ever hosted life on its surface, it couldn't endure the loss of its atmosphere or the relentless radiation that followed. If Venus once had oceans alive with possibilities, that life couldn't withstand the crushing heat and pressure that came later. Studying these limits tells us not just where life might thrive, but where it can't, and how close our own planet might be to those invisible boundaries. Another lesson from the graveyard is that timing can decide everything. If the asteroid that wiped out the dinosaurs had arrived a few million years earlier or later, the outcome could have been drastically different. If Mars had kept its magnetic field just a little longer, life there might have gained the foothold it needed to survive. Timing shapes not only a planet's history, but its very chances of ever developing life at all. We also like to believe that intelligence is the ultimate survival tool, that once life reaches a technological stage, it can protect itself from nature's worst disasters. And while that's true in part, civilizations create new vulnerabilities too. A world may have fallen not because it couldn't survive the universe, but because it couldn't survive itself. In a galaxy as vast as ours, it would be surprising if no such self-inflicted extinctions had occurred. If they have, those abandoned ruins would be among the most haunting artifacts in the graveyard of worlds. Another truth the Dead Worlds reveal is that no planet exists in isolation. A world's fate is tied to its star, its neighboring planets, its position in the galaxy, and the massive flows of matter and energy that sweep through the cosmos. A nearby supernova can strip away a planet's atmosphere. The orbital shift of a massive planet can destabilize smaller ones. Even a star passing through a dense cloud of interstellar gas can alter the delicate balance that life depends on. Survival, in other words, is never fully under a planet's control. Perhaps the most profound lesson they offer is humility. It's tempting to see Earth's story as inevitable, as if life here was always destined to reach this point. But the graveyard tells a different tale, one of countless promising beginnings that ended in silence. Our survival so far has depended on a chain of events so precise, so influenced by chance, that it's nearly impossible to imagine repeating it exactly. That doesn't mean it can't happen elsewhere, but it does mean it's rare. From a scientific perspective, Dead Worlds are more than cautionary tales. They're invaluable research sites. By studying Mars, Venus, and the icy moons of the outer solar system, we're learning how atmospheres change, how climates can shift, and how geological activity can support or destroy habitability. Each mission that maps their surfaces, studies their composition, or peers into their histories isn't just uncovering their past, it's revealing possible futures for Earth. Even without sending spacecraft, we can spot exoplanets that seem to be past their prime. Some show strange atmospheric chemistry hinting at climate collapse. Others orbit stars already shifting into less favorable states. Cataloging these cases lets us begin mapping the outer boundaries of habitability, the fine line between stability and decline. This knowledge isn't just theoretical. If we can recognize the early signs of a planet in trouble elsewhere, we might see them on Earth in time to act. If we can understand how others lost their stability, we might learn how to keep ours. The graveyard reminds us we're part of a far bigger pattern, and our survival depends on understanding it. But it also offers a perspective beyond the scientific. Dead Worlds show us that life is precious not because it's everywhere, but because it's rare. They remind us that each generation living on a thriving planet has inherited something countless others have lost. The graveyard may be vast, but it's not universal, and we're fortunate to be among the living. What we do with that fortune is the real question. If we treat our survival as guaranteed, we might end up as another silent entry in the graveyard's record. If we recognize our fragility, we might take the steps needed to extend our time here. The Dead Worlds can't choose for us, but they make it very clear what the stakes are. From here, the focus shifts to how we detect life and loss across the galaxy, how the faint signals we search for can tell us whether a planet is thriving, fading, or already gone, and how some of those signals might be hidden in plain sight among the stars we've already mapped. Day to day, it's easy to believe that Earth's conditions are fixed. The air we breathe, the climate we've adapted to, the ecosystems we depend on, we grow up within them, build our cities inside them, and take them for granted. But the reality is that nothing about Earth's present state is permanent. This moment in geological and biological history is as fragile as a soap bubble, and bubbles can burst. Right now, we're living in an unusually stable climate. For the past 10,000 years, temperatures and sea levels have stayed within a range narrow enough to support agriculture, the rise of cities, and the spread of civilizations across the planet. That stability is the foundation of everything we call modern life. Before it, the climate swung wildly between ice ages and warm periods. After it, it will inevitably shift again, whether through natural cycles or human influence. This stability isn't Earth's default state. It's an exception, the result of a set of factors that for now are aligned in our favor. Earth's axial tilt is steady enough to keep seasons predictable. The atmosphere holds in just the right amount of warmth without trapping too much. The oceans move heat around the globe in patterns that prevent extremes from dominating. Volcanic activity is relatively low, and the sun's energy output is stable. None of these conditions are locked in forever. All have changed before, and all will change again. Looking at other worlds makes the fragility of this balance clear. Mars lost its magnetic shield, and with it, the ability to protect its atmosphere from the solar wind. Venus may once have had oceans, but a mix of solar heating and atmospheric shifts pushed it into a runaway greenhouse. Even tiny changes in a planet's environment can unleash feedback loops that accelerate those shifts, sometimes making recovery nearly impossible. Earth has these loops too. When ice melts, it exposes darker surfaces that absorb more heat, leading to even faster melting. Thawing permafrost releases greenhouse gases, which warm the air further. Cutting down forests removes a key way for the planet to pull carbon dioxide out of the atmosphere, speeding up warming even more. While these loops can start naturally, human activity is now triggering and amplifying them at a rate nature can't keep up with. In geological terms, the changes we're causing are abrupt, a massive surge in greenhouse gases within just a few centuries, sweeping changes in land use and biodiversity in only decades. Earth systems are tough, but they're not unbreakable. Push them far enough, and they can flip into a new state, one that may not work for the civilization we've built. This fragility isn't just about climate. Our food supply depends on reliable weather, steady rainfall, and fertile soil. Our freshwater comes from glaciers, mountains, snow, and rivers that follow predictable patterns. Our cities, roads, and power grids are designed for specific ranges of temperature, wind, and flooding. A significant shift in any of these could cause cascading failures across the systems that support billions of people. The more interconnected those systems are, the more one failure can trigger others. Technology can help us manage some risks, but it also adds new ones. Our dependence on global supply chains means a disruption in one part of the world can spread everywhere. Our reliance on digital infrastructure leaves us exposed to power outages, cyber attacks, or communications breakdowns. Even advanced solutions meant to protect us, like genetic engineering or artificial intelligence, carry the possibility of unpredictable side effects that are hard to foresee or control. And beyond all that, there are forces we can't influence at all. A massive volcanic eruption could spew enough particles into the air to cool the planet for years, wrecking harvests. A large asteroid, though rare, could devastate the entire globe in a matter of days. Changes in the sun's activity could shift climate patterns in ways we're not ready for. All of these have happened before in Earth's history, and they will happen again. The only question is whether they'll hit us during a time of stability or instability. Every planet in the graveyard of worlds once had a present moment, a period when conditions were good enough for life to thrive. For some, that moment lasted millions of years, for others only a few thousand. But once it ended, it almost never returned in the same form. The loss might be slow or sudden, but either way it's nearly always permanent on human timescales. This understanding isn't meant to make us hopeless. It's meant to make us alert. Knowing we live in a rare, stable window shouldn't make us relaxed. It should make us careful. We have the ability to see warning signs, model possible changes, and take steps that could stretch out our current good fortune. Planets in the graveyard never got that chance. They couldn't debate or prepare. They simply followed the path their circumstances set for them. But awareness only matters if we act on it. Recognizing fragility is one step. Building resilience is the next. That means protecting the systems we rely on, reducing the stress we put on the environment, and preparing for disruptions that will inevitably come. It also means accepting that some changes are unavoidable, and that adapting to them is just as important as preventing them. In the grand sweep of cosmic history, our present moment is just a blink, but to us, it's everything. It's the window in which we decide whether Earth will join the graveyard sooner than it has to, or whether we can keep this rare balance going for as long as possible. The choice is still in our hands, as long as we remember how easily what we depend on can be lost. From here, the next step is to figure out how we detect the signs. The clues that reveal whether a planet is thriving, declining, or already gone. And those signs, when we scan the stars, may be far subtler than we expect. When we call Earth a planet in the Goldilocks zone, we mean it sits at just the right distance from the sun, not too hot, not too cold, for liquid water to exist on its surface. It's a neat and simple idea, one that has guided our search for life elsewhere. But the more we study planets, the more we learn that just right is far more complicated than a textbook diagram suggests. Being at the right distance from a star is just the starting point. Staying there, staying just right, is an ongoing battle, and one that many planets lose. The habitable zone itself isn't fixed. Stars grow brighter over time, shifting the zone outward. A planet comfortably inside it today might end up on the inner edge in a few 100 million years, with rising temperatures pushing it toward a greenhouse disaster. A planet on the outer edge could freeze solid if its star dims or its atmosphere thins too much. In other words, habitability is a moving target, a window that opens and closes. An atmosphere plays a huge role in whether a planet can stay inside it. Without enough atmosphere to trap heat, even a planet right in the zone will be too cold for liquid water. Mars is the obvious example. It's technically in the Sun's habitable zone, but its thin atmosphere leaves it frozen for most of the year. On the flip side, too thick an atmosphere can trap so much heat that the planet becomes a furnace, just like Venus. The just right balance a planet needs is incredibly narrow, and it's not just about where it starts, but how its climate and geology work together over billions of years. One of the most overlooked players in habitability is geology. A planet's internal heat drives volcanic activity, releasing gases into the atmosphere. Plate tectonics act like a climate regulator, cycling carbon between the surface and the deep interior. Without this geological thermostat, a planet might lose its atmosphere entirely or let greenhouse gases build until it bakes itself. Earth has enjoyed this regulation for most of its history, but not every world in the habitable zone is so lucky. Even water, the ingredient we often treat as the ultimate marker for life, comes with complications. Too much, and you get a world covered by a global ocean with no land to drive nutrient cycling. Too little, and life may never begin at all. And how that water is distributed matters. A planet might have polar caps with deserts at the equator, or be frozen solid with only small pockets of liquid deep underground. Water alone doesn't make a world just right. It's how it interacts with the planet's other systems that counts. External influences add yet another layer. Large moons can stabilize a planet's tilt, keeping seasons predictable but without one. Climate swings can become extreme. Giant planets in the same system can protect smaller worlds from asteroid bombardment, or destabilize their orbits entirely. Even a planet's location in the galaxy matters. Too close to the center, and it may be blasted by radiation from supernovae. Too far out, and it may lack the heavy elements needed to build rocky planets in the first place. When you put it all together, most planets never hit the right combination. Many are too small to hold an atmosphere, too geologically quiet to regulate climate, too unstable in orbit, or too unlucky with their star's evolution. And even those that start in the sweet spot might not stay there. The Goldilocks state isn't a permanent destination. It's a tightrope act the universe keeps trying to shake. For astronomers, spotting an exoplanet in its star's habitable zone is only the first step. To know if it's truly just right, we'd need to know its atmosphere, geology, water cycle, orbital stability, and how all of that has changed over time. Without that, habitable zone is really just a hopeful label, not a guarantee. And there's a timing problem. Life, especially complex life, takes time to evolve. A planet might pass through a habitable phase too quickly for ecosystems or civilizations to develop. Or it might spend billions of years stable, only for some sudden change, a shift in the star's brightness, a massive impact, an atmospheric collapse, to wipe it all away before intelligence ever appears. Earth itself may have come dangerously close to missing its chance. Our planet has survived asteroid strikes, ice ages, and massive volcanic events without tipping into a permanent, uninhabitable state. That's partly luck, partly feedback between our systems, and partly timing. Many worlds never get that combination, or keep it for long. The Goldilocks problem is a reminder that planetary failure doesn't require total catastrophe. One key factor drifting out of balance can start a chain reaction. Temperatures don't have to climb to Venus levels or drop to Mars levels. Even smaller shifts can make life harder and harder to sustain. Habitability isn't a simple on-off switch, it's a spectrum, and planets can slide the wrong way slowly or all at once. The more we study it, the clearer it becomes the balance we enjoy now is rare, temporary, and under constant threat. The habitable zone will move. Our atmosphere will change. The forces that keep our climate stable will be tested again and again. We can't stop the big cosmic shifts, but we can work within the time we have, using what we've learned from other worlds to keep ours balanced for as long as possible. The question is whether that knowledge can actually tilt the odds in our favor, or whether Earth is simply another world waiting its turn in the graveyard. When we look at the graveyard of worlds and the razor-thin conditions needed to avoid joining it, it's tempting to see ourselves as the lucky exception, the planet that beat the odds, that found the right balance, that stayed just right long enough for intelligent life to appear. And in many ways we are. Earth's history is a chain of improbable events, each one linking perfectly to the next, any one of which could have broken the sequence and left our planet with nothing more complex than mats of microbes clinging to shallow seas. But the real question isn't whether we've been lucky so far, it's whether that luck can last. Every world in the graveyard was once the lucky one. Mars had rivers. Venus may have had oceans. Countless others, orbiting other stars, likely enjoyed periods of stability that made them seem destined for longevity. None of them kept it. The difference between being the exception and being the next in line isn't how you start. It's whether you can hold the line when the universe starts pushing back. And the odds are never fixed. Earth's survival so far doesn't guarantee its future. We're still vulnerable to the same forces that reshaped Mars and Venus, to the same catastrophes that can strip a planet of life, to the same slow drifts toward instability that can make a world unrecognizable over geological time. The only difference is that we know these dangers exist, and in theory, we can prepare. That awareness is a double-edged sword. It gives us tools to defend ourselves. We can track asteroids, monitor solar activity, model climate change, and build systems to adapt. But it also gives us unprecedented power to destroy our own stability. We can alter the atmosphere on a planetary scale, erase species at a rate rivaling mass extinctions, acidify oceans, and build weapons capable of ending civilization in days. Intelligence, our great advantage, is also our greatest risk. Civilizations, at least on Earth, tend to grow until they strain the systems that support them. In the past, those systems were local, soil fertility, fresh water, forests, fisheries. Today, they are global. The atmosphere, the oceans, the biodiversity of the entire planet. We are drawing them down at a rate that would be unsustainable even without climate change accelerating the pressure. The graveyard may not be filled only with natural failures. It may also hold the ruins of civilizations that crossed invisible thresholds too slow to realize they had no way back. If life is common, and intelligence emerges even rarely, then statistically there have probably been others like us, aware of their fragility, capable of action but not guaranteed to succeed. The danger is assuming we're different. Technology and knowledge don't save us automatically. They only work if we act in time. And history shows that recognizing danger doesn't always mean responding before it's too late. And yet, the very fact that we can imagine the graveyard, that we can place ourselves in its shadow, is a kind of hope. No other species we know of has modeled planetary-scale risks or deliberately tried to change its trajectory. If we can anticipate the forces that threaten habitability and counter them, maybe we can extend our time as the exception far beyond average. But awareness and effective action are not the same thing. The timescales of planetary survival are vast. Small miscalculations today can have consequences centuries or millennia from now, long after their cause is forgotten. And some forces are beyond any control. We can't stop the sun from brightening, or prevent a nearby supernova, or halt the slow cooling of Earth's core. We can adapt, maybe even offset some of these changes, but no planet stays habitable forever. The real question isn't whether Earth will join the graveyard. It will, but when and whether we'll be the ones who push it there sooner than necessary. In truth, every living world is already on the slope toward that fate. Some are just beginning their habitable moment. Others are already sliding past the point of no return. And some, like us, are balanced on the edge, in a position where the next few centuries may decide the direction of the fall. That distinction between exception and next in line isn't a permanent identity. It's a temporary position, held only as long as a planet's systems remain within the narrow boundaries of habitability. Those boundaries are constantly under siege, and the outcome depends on how well we balance natural cycles against our own impacts. The unsettling truth is that we may not know the tipping point until it's behind us. A slow decline can feel like stability right up until it crosses an irreversible threshold. Many worlds probably ended not with one great catastrophe, but with a series of changes that seemed manageable until they weren't. But that's also where the opportunity lies. If we can recognize those warning signs early enough, if we can learn what decline looks like before it becomes fatal, we might act in time. That requires more than technology. It requires a shift in priorities, choosing long-term planetary stability over short-term growth. It's a change no civilization has ever attempted on a truly global scale. But it may be the only way to remain an exception longer than most worlds ever manage. Whether we succeed or fail will become part of the record, just as Mars, Venus, and the countless lifeless worlds beyond our sight have their own stories etched into the graveyard. One day, future explorers, human or otherwise, might look back and see Earth as the rare example that lasted far longer than expected, or they might see us as just another world that didn't realize how close it was to the edge until it was already falling. And that brings us to the final question. What signs will we leave behind? What traces will tell the next observers whether we endured or whether we joined the silent majority in the graveyard of worlds? When a massive asteroid or comet slams into a planet, the immediate aftermath is destruction, but over longer spans of time, it can become an act of redistribution. Shattered rock, ice, and even organic molecules can be blasted into space, some traveling across light years before finding a new home. Occasionally, those fragments land on other worlds, carrying with them the chemical seeds of life. On Earth, we've discovered meteorites that originated on Mars, pieces of another world that drifted across millions of kilometers to end up here. If life ever took root on Mars, it's possible, though unproven, that traces of it could have survived such a journey. In that way, a failed planet might still contribute to another's success. Even without violent collisions, dead worlds can influence their neighbors. A planet with a bright reflective surface might alter the light reaching its moons. A migrating gas giant could scatter other planets into new orbits, reshaping climates and tipping the scales between habitability and sterility. No planet exists in isolation. Each is part of a web of gravitational interactions capable of rewriting the fate of entire systems. Some failed worlds might still remain valuable long after their surfaces have frozen over. Far from their stars, certain planets could hide vast subsurface oceans, kept liquid not by sunlight, but by the slow release of radioactive heat, or the tidal pull of a nearby giant planet. Moons like Europa and Enceladus show us that icy crusts can conceal active, possibly life-friendly environments. From a distance, these worlds may seem lifeless, yet beneath their frozen exteriors, something extraordinary could be waiting. And then there's the possibility of revival. We often picture planetary habitability as a one-way slide toward extinction, but certain conditions could tip it back the other way. A frozen planet could thaw as its star brightens, or as orbital changes draw it closer to warmth. A world stripped of its atmosphere might slowly build a new one through volcanic outgassing, or the impacts of volatile-rich comets. These changes are measured not in centuries, but in millions or billions of years, a timescale the universe has no trouble accommodating. From that perspective, 1 billion years in the graveyard could be nothing more than an intermission. For advanced civilizations, even failed worlds could be opportunities. A lifeless planet might still hold valuable metals, frozen reservoirs of water, or a strategic location for exploration. To a technological species, the graveyard might not be a cemetery at all. It might be a resource map. Some futures are even more ambitious. If a civilization becomes advanced enough, it could attempt to restore a planet's habitability, importing an atmosphere, steering comets to deliver water, or building vast structures to regulate climate. These concepts, filed under terraforming, remain far beyond our reach today, but nothing in the laws of physics forbids them. If someone chose to intervene, a failed world could be brought back from the brink. But intervention raises difficult questions. If a planet once hosted life, would restoring it disrupt whatever might have evolved in its absence? Could a revived world remain stable for the long haul, or would it inevitably slip back into the same conditions that doomed it before? The graveyard itself can't answer these questions, but it can give us examples to study. Even after a world loses surface habitability, it leaves behind a geological archive. Oceans, rivers, and forests may be gone, but fossils, mineral layers, and isotopic traces remain, telling the story of what once was. For future explorers, these worlds could be museums preserving the history of life in stone and ice. In the cosmic cycle, nothing is truly lost. It changes form. A dead planet can become a moon, part of a ring system, or raw material for the birth of new worlds in a distant star's nursery. The line between living and dead worlds is blurrier than we think. Even the loneliest rock drifting between stars carries the imprint of its past and the potential to influence another system's future. This perspective reshapes how we think about our own distant fate. When Earth eventually becomes uninhabitable, whether in hundreds of millions of years through natural change or much sooner through our own mismanagement, it won't simply vanish. Its atoms will scatter, some perhaps becoming part of new planets, new moons, even new biospheres. Our world story will continue in ways we cannot imagine. The graveyard is not the end. It is a point of transformation. A world that appears dead today might have thrived yesterday, and might do so again tomorrow, in cosmic terms. Studying those worlds could teach us how to protect our own, how to keep habitability going for longer than chance alone might allow. Perhaps that's the graveyard's most important lesson. Failure is only final if we define it that way. If we see it instead as a change of state, part of a larger cycle that can open the door to new possibilities, then no world is truly finished. It becomes something else, and in becoming something else, it remains part of the living universe. From there, the view naturally expands. The question is no longer what happens to one world, but what the graveyard as a whole reveals about the life cycle of planets, and what that means for our understanding of the cosmos itself. Step far enough back, and the pattern is clear. The graveyard is not rare. It is the rule. The number of planets still clinging to that fragile balance that sustains life is almost certainly dwarfed by the number that have already lost it. That reality doesn't make the survivors less remarkable. It makes them all the more extraordinary. And in that light, our own position, on a still living world, tested but enduring, is both humbling and fragile. We've survived asteroid impacts, ice ages, and mass extinctions. We've reached a point where we can study our planet's past, model its future, and see our vulnerability with clear eyes. We've also introduced dangers to our world that nature alone might never have unleashed. Threats that could unravel our stability far faster than the cosmos would have managed on its own. The graveyard reminds us that no matter how fortunate a planet's start, change will come. Stars evolve, orbits drift. Atmospheres leak into space or thicken until they choke life. Worlds grow colder, hotter, or are reshaped in an instant by collisions. Some of these shifts unfold slowly enough for life to adapt. Others strike too quickly for survival. The real difference between a thriving world and a failed one isn't where change begins. It's how well a planet's systems can respond. For Earth, those systems are no longer purely natural. Humanity has layered its own influence over the planet's mechanics, an influence that can be a shield or a sword depending on how we wield it. Our technology can detect incoming hazards, restore damaged ecosystems, capture carbon, or cool our cities. But it can also drain resources faster than they can be replenished, throw climate systems off balance, and create vulnerabilities we never had before. The same tools that could keep us alive could also be the very ones that end us. The graveyard teaches that lasting habitability is never passive. No planet remains stable for billions of years by luck alone. Even the most favorable start demands ongoing balance between geology, atmosphere, and orbital rhythms. For a world with intelligent life, survival also hinges on the decisions that life makes, how it treats its environment, how it shares its resources, and how it prepares for disruptions it knows will come. The moment we stop making those choices with intention is the moment our descent toward the graveyard accelerates. There's another lesson here, harder to measure, but just as vital: perspective. Seeing ourselves as one world among countless others, part of a timeline that runs from lifeless origins to inevitable endings, changes the scale of our daily concerns. Yes, our current problems are urgent, but they're also part of a much larger pattern. The same forces that will one day strip away Earth's habitability are the forces that made it possible in the first place. The challenge is to make the most of the space between those 2 points. Being among the living is more than biology. It's also about awareness, the rare ability to imagine our own extinction, to recognize the warning signs of decline, and to think about how to prevent it. That awareness is itself a kind of survival mechanism, one no other species we know has ever possessed. It offers us a chance, not certainty, but a chance. If we fail, we'll become part of the graveyard story. Our cities, satellites, and the geological traces of our time here will become artifacts for future explorers, human or otherwise, to examine. They might wonder how long we endured, what mistakes we made, and whether we saw the end coming. Perhaps they'll view us as a rare species that defied the odds for far longer than expected. Or they might see us as yet another example of promise squandered, a world that never realized how close it was to the edge until it was already falling. For now, though, we're still here, breathing the air, walking the land, looking up at the sky that still shields us. Our oceans still circulate, forests still grow, ice caps still wax and wane with the seasons. We still have the ability to act, to adapt, and to imagine futures in which we extend our time among the living. That's a rare position, and it's one we shouldn't take for granted. Our place among the lost will arrive eventually, in cosmic terms, sooner than we'd like. The graveyard is patient. It can wait billions of years. The question is whether we'll reach it because the universe finally forces our hand, or because we let ourselves drift there through negligence, conflict, or refusal to act. One of those paths is unavoidable. The other is not. Which one we take is still up to us, but not forever. So perhaps the clearest truth to carry forward is this. We are both survivor and candidate, a world that has endured against staggering odds, and a world that could still join the silent majority if those odds turn. Seeing that clearly might be the most important insight we ever possess. Because only with that clarity can we choose whether our entry into the graveyard comes far sooner than it must, or far later than anyone would expect. From that choice, everything else follows, not just for us, but for the story our planet will tell long after we're gone. And if you've stayed with me through this journey, thank you for giving your time to reflect on our fragile, astonishing place in the cosmos. The graveyard of worlds is vast, but for now we're still here. Let's keep it that way for as long as we possibly can.